To make the connection between area and probability, let's look at a continuous probability distribution called the uniform distribution. In a uniform distribution, the values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So let's look at an example. At a salad bar, customers are charged by the weight of the salad they choose. Sampling suggests that the amount of salad taken is uniformly distributed between 5 ounces and 15 ounces. The random variable x represents the weight of the salad, and the probability for each value from 5 to 15 ounces is equally likely. So let's see if we can get a graph started on what this might look like. Okay, so as we said for these probability distributions, our vertical axis is probability and our horizontal axis is our random variable x. So this is the probability of the random variable x. Okay, so we're told that the values range from 5 to 15. So I'll say this is 0. Here's 5. About here would be 10. And about here would be 15. And these are ounces. So this is the salad weight in ounces. Okay, so we're told that the probability for each value from 5 to 15, and there are an infinite number of values between 5 and 15, all the fractional parts of ounces in between here, and this is equally likely. Okay, so that means it's the same probability. This value here on our probability scale from 5 to 15 is the same. Okay, so this is where we get that rectangular shape. Okay, so what is this equally likely probability? Where are we on our vertical scale if this is the case? Well, recall that we said we have a probability of 1. The area under the curve must equal 1. So let's make note of that. Total area under the curve is 1. And the curve is a rectangle. And so the area of a rectangle is equal to length times width. Well, if I already know that the area is 1 and my length is this dimension, so it would be, I would get that by taking 15 minus 5 to give me this length of the rectangle, times, well, width is what I'm looking for. The width would be this probability here. So now I have one variable and I can solve this equation. So 1 is equal to 10 times W. So I would divide both sides by 10 to get that the width then is 0.1, or a probability of 0.1. So now I can come back over to my graph and label that 0.1. Okay, now I know that equally likely probability for any of these values in between 5 ounces and 15 ounces. So that means that we would expect any of these ounces, any ounces measurement between 5 ounces and 15 to have a probability of 0.1. Okay, so this graph, another name for this graph of a continuous probability distribution, is a density curve. So our continuous probability distributions are the uniform, we're talking about that one now, we'll be talking about the normal distribution. So there are specific requirements for a density curve. Let's look at those for a minute. Okay, requirements for a density curve. First, the total area under the curve must equal 1, very important. And the second is that every point on the curve must have a vertical height that is 0 or greater. The curve cannot fall below the x-axis. So what are these telling us? They're telling us the same thing we learned about probability. The total area under the curve, remember the total value of the sum of the probabilities in the sample space must equal 1. Same thing. Here we're saying every point on the curve must have a vertical height 0 or greater. With what we said before when we studied probability was that probability can be 0 or larger than 0 up to 1, right? But it could never be negative. So this is just continuing that understanding of probability. Okay, so let's go back to our example, our graph. Okay, and we don't need our calculations there anymore. So now we can look at what this graph can help us do, what kind of questions we can answer using the graph. So we can use our understanding of the correspondence between area and probability to find particular probabilities. So say we wanted to find the probability that a randomly selected customer at this restaurant would purchase a salad with a weight greater than 7 ounces. So let's see, let me write it over here. Probability, oops. We want the probability that the weight is greater, I'm going to abbreviate weight greater than 11 ounces. Okay, so what I'm saying here in more shorthand notation, that's the probability that my random variable x is greater than 11. Okay? Okay, well, what I'm looking for then here is the area of the shaded region greater than 11. So let's see, 11 would be approximately right here. So here's the probability. Whoops, kind of crooked. I'm trying to get a straight line. That's pretty bad. Okay, I'll shade this way. This is my shaded area here. So that area represents the probability that a randomly selected customer would choose a salad that weighed more than 11 ounces. Okay, so recall that this area then would be, here's its width. I'm sorry, here we'll call that the length because we were calling this the width before. And here's its width. And so the area is equal to length times width. So that's the same, this probability that x is greater than 11 will be this length, which is 4, right? From 11 to 15, that's 4. So it would be 4 times, and we already know that probability, 0.1 or 0.4. So there's a 0.4 probability that a randomly selected customer would choose a salad weight greater than 11 ounces. So we're making that connection here between area and probability. And then our last step when we're asked a problem like this is to give our interpretation. And so we would say something like the probability of randomly selecting a customer whose salad weighed more than 11 ounces is 0.4. Okay, that's an interpretation of our result in a nice sentence. Now, why didn't we ask the probability of a randomly selected customer whose salad weighed exactly 11 ounces? Well, let's think about that. If our values can be anywhere between 5 and 15, then exactly 11, not 11.01 or 11.02 or 10.99, but exactly 11.000 ounces, the chance of that occurring is so very, very small that when we deal with continuous probability distributions, we are not interested in the probability of an exact value for X. That exact value for 11 ounces is just infinitesimally small, and we wouldn't be interested in that. So we'll be looking at probabilities that are greater than, less than, or between two values, instead of the probability of an exact value. Okay, so just kind of quickly to summarize that, I would say we will be looking at things like the probability that X is less than some value A, or the probability that X is greater than some value A, or the probability that, say, X is between two values. So we could say, you know, the probability a randomly selected customer has a salad weight between 6 and 8 ounces, okay? Or we can say greater than 11, or we could have said less than 9. There's just, depending on what we're interested in. And one other thing to note, since the probability of exactly some value is extremely small, we will say that these are the same as, sorry about that. Let's see if I can fix that real quickly. Okay, these are the same as saying the probability that X is less than or equal to A, the probability that X is greater than or equal to A, and the probability that A is less than or equal to X, which is less than or equal to B. We won't get a different answer because that or equal to part is so small, it's too small to really be detected. Okay, so that's a quick summary of the uniform distribution. We look at that primarily to get that understanding of the correspondence between area and probability. Next, we'll move on to the normal distribution.